Swayam Prabha. Digital India. Educated India.
Okay, I guess we'll get started. We have, I kind of left you hanging at the end of the previous lecture, but we'll cover that now. Okay, so the plan for this lecture, actually I'll start with defining security of encryption. So we didn't quite do that. We talked about perfect secrecy, but that would work only for one-time encryption. So we'll start by defining security. It has a particular name, this kind of security that we'll be interested in. So security of symmetric key encryption. It's called CPA security, chosen plain text attack security. So I'll define that first. And then I'll get to where we left off, how to do encryption using a block cipher. Okay? And then we'll talk about authentication. So that'll be the kind of the second half of this lecture. And we'll end with some discussion about ciphers as used in practice, and that's what you'll do in the session after this, the lab session, right? And something I was planning to cover right now, but we'll probably keep it for a little later, is how do you build this PRG and PRF? In practice, it's kind of a heuristic process. In theory, there is some sound way to do that, and if, we'll do that later, maybe tomorrow. Okay, so let's start with perfect secrecy. Go back to that definition, but I'll define it slightly differently this time. Okay? So here's again an experiment, but it looks like a slightly different experiment. It's actually the same thing, but it's not the same thing. It is equivalent. So here is a new definition, new experiment. Okay, so there is an adversary and there is an experiment. Okay, it's a process. I'll draw these kind of blue boxes to say what's happening in this experiment. And what the experiment does first is pick a random bit B, uniformly random. And as you know, at the end of the game, we are going to check if the adversary manages to guess this and look at the advantage of guessing this bit. We have an encryption algorithm. I've drawn it outside. It's part of the experiment, but it has been set up with a key already. So you uniformly randomly generate the key, or whatever is the encryption algorithm's key generation scheme. You generate the key, and here's where things are a little different. You ask the adversary to give you two messages, any two messages of its choice, M0 and M1. Okay. These, of course, should be messages from the message space that's implicit. So the encryption scheme is for some message space, and these two messages should be from that message space. And what the experiment does is picks one of these two messages. Which one? Well, whichever one the bit B suggested, right? So if B is 0, you pick M0. If B is 1, you pick M1. So basically, the experiment is picking one of these two messages uniformly at random. And it will encrypt that message and give it to the adversary. Okay? Encrypt using this key that was already picked at the beginning of the experiment. And the adversary has to guess B, so it outputs a bit, which I'm calling B prime here. And the advantage of the adversary is, so the perfect secrecy says the advantage should be 0, so that basically says the probability that B equals B prime is exactly half. Okay? So B prime should be independent of B. Okay, so this was our definition for, there's an equivalent definition of perfect secrecy. So any questions on this? So, we are allowing the adversary to pick any two messages of its choice. So it would seem like, the adversary has to be kind of cleverer, right? Because maybe it's only for some particular pair of messages that the distributions are different, then it'll have to pick those. But the security definition says for every adversary, so in particular every choice of M0, M1 that the adversary could pick, the advantage should be 0. Okay? So whether you encrypted M0 or M1, the ciphertext distribution should look the same. Otherwise, an adversary can, can get some advantage here. Okay. So we're going to change this definition a little bit. By the way, any question? Because it's not necessarily, immediately apparent that this is the same definition, but trust me, it is. But if you have any questions, you can, yeah.
What does it mean that the experiment implies the adversary with encryption?
So that's how I'm defining the experiment. The adversary can send me a pair of messages. I'll pick one of them, I as the experimenter, encrypt it using this key that I already picked, and give it to the adversary. So the adversary knows M0, M1, it picked it itself, it got a ciphertext, and it's trying to guess if the ciphertext is for M0 or for M1. Okay. The message is, one important thing is that we are not picking the messages. We are not saying we'll pick the messages at random. The adversary gets to give me 2 messages. Okay. And a really bad idea for the adversary would be to pick M0 and M1 to be the same message, because then obviously the ciphertext is distributed the same way. It's independent of the bit B. So somehow intuitively the adversary is trying to get some 2 very different messages which should show up as different in the ciphertext, but hopefully our scheme will give the same distribution of ciphertext. Yeah.
So is the multiplexer scenario involved over here?
No, this is all the experiment is. This is the definition of perfect secrecy. Okay. Now we want to upgrade from this definition, or actually downgrade from this definition by going down to computational secrecy instead of perfect secrecy, but upgrade by requiring security against multiple encryptions. Okay, so the previous one only allowed the adversary to get one ciphertext. Now we are going to allow the adversary to get multiple ciphertexts. Okay, so starts off as before, the experiment picks a bit B, but now for as long as the adversary wants, it will pick a pair of messages. So each time it can pick a different pair of messages. We will pick MB out of it. So B is fixed throughout, and we will encrypt this MB, right? And give it to the adversary, and the adversary can keep repeating this. So the key and the bit B are fixed. The adversary can adaptively look at the previous ciphertext, pick a new pair of messages, get one of them encrypted, doesn't know which one, and keep going, and then at the end it has to guess as before. It tries to guess which bit B is. Okay? And now the advantage is defined slightly in this weaker form. We only restrict to adversaries which are feasible. Okay, so the adversary has to be efficient algorithm, and also we allow a little bit of slack. We don't require that the adversary's advantage is 0. We allow the adversary a very small or negligible advantage. Okay? So that's our new definitions. So it's probably kind of a little deeper than what it would seem. You could stare at it for longer and kind of get more out of it. But any quick questions before we move on right now? Okay. Okay, we'll come back to this later. Okay, now now that we know what the definition of symmetric key encryption that we are after is, how do we do it? How do we get it using a PRF or a block cipher? And we'll first consider the situation where there is a single block of message. Okay, so here is how it goes. This key for the encryption is going to be the key or the seed for the PRF, okay, for the block cipher. And I'll have a picture shortly. But for each time Alice is going to encrypt, so Alice is trying to encrypt multiple messages, right? It could be actually the same message being encrypted multiple times, but she's doing encryption multiple times. And each time she should pick a fresh pseudo-random pad. How does she do that? She picks a new value R, a value, so it's a input to the block cipher, which has not been used so far. So she'll pick a new value R and feed it into the block cipher. Her key always stays the same, and she gets a pad. and then this is what she is doing. So she picked a she picked a new value r, she used this key and generated a pseudo-random pad, then that's XORed with the message. And here the message is a single block meaning whatever is the output size of this block cipher. Okay? And so far this looks a lot like what we did with stream cipher. An important difference is that there is this R now, right? How do you decrypt? Well, what do you mean by you'll do reverse? We have the key, we have the ciphertext. XOR with what?
So that block is creating a key for the next block, right?
There's only one block here. Don't worry about it. There's only one block. We are encrypting a single block. Question is, how do you decrypt this ciphertext? You had a suggestion?
So in case of multiple block scenarios,
First, we have to figure out how to decrypt one block before we,
yeah. So for the one block, I could use the M from the previous block
There
as
is-
an input for R.
But how will you then do the first? I mean, okay. So you have some things you have seen in mind. Forget all of that. Okay. This is because a lot of those things are also confusing, if not misleading. So let's just start from scratch. This is a very simple situation here. So far, I have said how I create this one-time pad or pseudo-random pad and XOR it with the message. To decrypt, you somehow need to create this pseudo-random pad, right? Then you can unmask it. But what's preventing, or what does the decryptor need to do that? What does a decryptor have?
We have the ciphertext.
It has a ciphertext.
We have the key.
It has a key. Is that enough? Okay, we need R. Where is it going to get this R from? Because you pick it's a random R that the encryptor picked. Okay, so this is not good enough as a ciphertext. You need to also send this R. So if you send this R also, then you know what to do. You take this R, feed it as input into the block cipher. You get the pad that you can then use to unmask the ciphertext. Okay. All right. So is this going to be secure? I mean, this R is kind of in the clear, right? Is that a problem? Well, it's not a problem because what PRF tells you, or what block cipher, or when you modeled it as a PRF, what we know is that even if you see many input-output pairs to the block cipher, remember, I don't have the picture for that here, but when we define the block cipher, an adversary gets oracle access to the function, which could either be the block cipher or a truly uniform random function, right? So what does it mean to have oracle access? It can see inputs, it can feed inputs, get outputs. So even if that adversary sees as R, which is the input to a block cipher, gets the output, it cannot really tell if the output is a uniform random string or something that came out of the block cipher. So imagine for a second we are using uniform random strings. So you feed R from the block cipher, or instead of the block cipher now we are getting a uniformly random string. But if that's what we were doing in this encryption, if we are using a uniformly random string here, so forget our key, forget the entire block cipher, it's just a uniformly random string. Well, then the eavesdropper has no information. Seeing this R went as input to the random function, but it doesn't have access to this function, right? I mean, we are not going to tell it, what the output is for this R. So this is a fresh R, meaning this R is never going to be used for anything other than for creating this one ciphertext, so that the eavesdropper doesn't get me to tell it what the output of this block cipher is on this R. So for all that it knows, this R was fed into a random function and you got a random string as output that was used to mask, and I'm never going to tell it what that random string is. Okay? Yeah.
It's more, so I'm more of an observation than a question.
Sure.
I'm not sure if I'm correct, but this R, So is this R a nonce, or because it feels to me it feels more like a secondary key. So can't you just have a number of variables that go in other than R with the key?
Okay, so you can hold on and we will see more things about this R. For now, all that matters is that this R is not used for anything else into this block cipher. It's not fed into this block cipher. So if you are holding the key of the block cipher, you pick this R, used it for this encryption, you will never feed this R into this block cipher again and answer something or use it for another encryption. So this R, it's called a nonce. Okay, so that's kind of a technical term, something that's a random string, or it doesn't have to be random really. Something here that's just fresh, that's used only once. Okay, but here it's not important that it's random. It's just something different each time. That's all that's needed. Okay, but how do you pick this R that's different each time? If you use the same R twice, then basically we're going against the one-timeness of one-time pad, right? You're using the same pad to encrypt multiple messages. So we don't want to use the same R twice. How do we ensure that we are using each R only once? Well, one option is you just keep track of all the R's you ever used, right? You just have a big database of all the R's that you ever used. That's not a good idea. In fact, that's kind of the same situation we were in with the stream cipher that we wanted to get out of. We didn't want the encryptor to keep a state, right? Keep updating a state. Here it's even worse. It has to store this increasing state. So that's not a good idea. But it would work, but not a good idea in terms of efficiency. What else can we do?
Change the function itself. Can we change the function?
Which function?
The generator pseudo-random function.
No, I want to use my block cipher. So it's a pseudo-random function. So I'm not changing the whole system. All I want to do is this thing. I want to pick a new R each time.
Maybe keep track of the previous R and increment.
Okay, that's a good suggestion. You could keep a counter so that you don't have to keep track of everything you ever used. You just need to know the last one you used so that you can take the next one. Okay, that at least kind of brings us back to the situation we were in with the stream cipher. Right? We just need to keep track of something. But we don't want that, right? We want to do even better. Use something like a time, like a timestamp, right? That could work. And it's a solution that depends on various external things, right? That you have a timer that will, not be wound back. It will keep going forward. You have to have any other suggestions? I mean, the counter, the timer, all those work, but something simple which doesn't depend on maintaining state or some external input. Yeah. Okay, not quite. So pick R at random. Okay. So you're saying random number generator, which is, you want it to be a pseudo-random string. You don't have to have that. For that, you'll need, pseudo-random, you're kind of back to the same problem. That's kind of what we are doing, right? You'll need a seed, you have to, so you don't really need a long string or anything. Just pick a fresh random string. So you have coins, you toss coins. Right? So that's a model of computation. You have access to random bits. So that's, what's that again? That is not, first of all, it has multiple issues, right? You have to maintain some state, but also, how do you, what's the first one, what's the second one? Like, what are you thinking of as the first and second ones? And also, once you have something which is a XOR of everything, you XOR it with that, you'll get the zero string. So that's not what we want. We want something which is fresh, which is different. So you cannot keep. It will become 0, 0, after the first, however you define the first two things, it will become, the third one will be 0, 0, or fourth one will be 0, 0, all zeros. And then on it will just be all zeros, right? You're XORing everything together, you get 0, you get 0. So, so you don't want to, but more importantly, you could imagine doing some complicated function of all the R's that you used, but for that you need to store some state about all the R's you used. Which, a better thing would be just use a counter, right? So you just need to know the last one you used, you just increment it. But the point is, you can pick one at random. Why does that work? If you pick one at random, there is a small chance that actually you'll pick something that already was used. But that chance is, say, this one block, the input to the block cipher is 128 bits. That chance is 1 in 2 to the 128. This is astronomically small, right? We don't care. Because these kind of, there are much higher probabilities that an adversary can guess your key and distinguish between a block cipher and a real random string. Right? So we don't care about this, tiny probability. That's exactly what we mean by very small. So picking a new R, picking a random R will up to a negligible probability give you a fresh R. Okay, and even if you've used several R's, even if you used millions of R's, when you pick a fresh R, that million is million out of 2 to the 128. That's still a tiny fraction. Okay? So you're safe if you can pick a fresh R, pick a random R. Random R is not needed at this point, but it would work. Okay, so that's what we are going to do for this. So far, just encrypting a single block of message. This key is a seed. The encryption, the ciphertext looks like this. You pick a random value R, and you set the ciphertext to be this. Okay, and how do we know this satisfies the security definition that I showed you? Well, the idea is similar to what we did for the stream cipher situation. We kind of want to say, look, using a pseudo-random function is indistinguishable from using a random function. And so that's the first thing here, right? If instead of using the ciphertext being the m XORed with the output of the pseudo-random function, suppose it was m XORed with the output of a random function, it will be indistinguishable. That's what the PRF guarantee gives you. And on the other hand, sorry, that's the second slide here, second bullet here. And on the other hand, if you actually picked a random string each time, so output of a random function is a random string. If you pick that each time, then the adversary has no information about the message. It will have zero advantage. Okay? So put together, what this means is that the adversary only has a negligible advantage. The negligible comes from this the one here. The PRF is only almost same as a random function. It looks almost the same as a random function, right? So that's a negligible difference. So any questions on this so far? Encrypting a single block. Okay, using a block cipher. This is what you should be thinking of when you want to encrypt using a block cipher. The block cipher is used to generate a random, pseudo-random pad, which you then use to mask, or which you then use as a one-time pad. Okay, and the care needs to be, put in to make sure that you are using fresh inputs to the pseudo-random function. So one thing here is that the encryption algorithm here, unlike one-time pad, and the encryption algorithm here is randomized. I said it didn't have to be random, it's enough to be different, but if you think of it as a closed system without maintaining state, each time you invoke the same encryption algorithm, if you're invoking it with the same key and the same message, we want it to behave differently each time. Maintaining state would be one way to do that, but if you don't want to maintain state, it has to be randomized. Okay? So for CPA security, for an encryption algorithm, in the sense of an encryption algorithm without state, it has to be randomized. So why is that the case? I mean, I said it has to be randomized, but what could go wrong if you use a deterministic encryption algorithm? How can an adversary in the CPA security game get advantage, like big advantage? if it's a deterministic encryption algorithm. So maybe I'll show you the definition quickly. Right? So here, what would go wrong if that encryption algorithm there is deterministic? So intuitively, what goes yeah, correct?
If the adversary has the access to two or more encryption outputs, then they can use that to guess information about the messages, like was in the XOR case.
No, I mean, but how? Like you'll have to, like, I'm saying it's a complicated algorithm here. We have no idea what it is. All I'm telling you is that it's deterministic. So each message you encrypt, it gives you some completely different thing. Now how do you use it? But this definition, so actually there are deterministic encryption algorithms for some special scenarios when you have random or entropy in the message. Okay? But we are trying to build a general purpose encryption algorithm here. We don't want to make any assumptions on message distributions. That's why we let the adversary pick any pair of messages. It's chosen plain text attack, so the adversary is choosing the plain text. So the intuitive reason is that if it's a good encryption algorithm, I shouldn't be able to tell if you encrypted the same message twice or two different messages. I see two ciphertexts, I shouldn't be able to tell if they are of the same message or not. And clearly if it's a deterministic encryption algorithm, I can tell. They will both look the same. And how does this definition capture this fact that if you see that you shouldn't be able to tell the difference between encryption of two, say, the two messages being the same or being different? Well, you could imagine an adversary, let's say, picks some two different M0, M1 in the beginning, gets the ciphertext for MB, and then it picks M0, M0 and feeds it. And it knows it will get the encryption of M0. Now it got the encryption of MB, it got the encryption of M0, and if they are equal, B is 0, if they are not equal, B is not 0. Okay? So this definition does capture that aspect also. Of course, it captures more. But in particular, and to be CPA secure, you cannot be deterministic. Okay. There's another thing I want to observe here, which is that we said we are picking the value R at random, but it was only so that they are different, right? So we seem to be not using, the full power of the PRF, right? PRF doesn't really require you to use a random value here. Or put another way, we are using more than what we need. We don't really need this full power of the PRF. We can certainly afford to pick random values. Even if the PRF said, I don't care, we can still pick random values. So maybe we don't need a full-fledged PRF. We can work with something which is a little weaker, a weak PRF. What's a weak PRF? It's exactly the same as a PRF, except instead of the adversary picking the queries to the oracle, we pick it. We as in the experiment picks it at random. We do show it to the adversary. So the adversary gets to see the query and the challenge and the answer as before. And sorry, I'm not sure. Oops, sorry, I killed the whole thing. I just wanted to okay, so the weak PRF is exactly like a normal PRF we defined, except that the adversary doesn't get to pick the queries. We pick the queries at random. The adversary only gets to see them. Okay, so this is good enough for getting our encryption. Our block ciphers or PRFs we'll have use for that shortly. But for what we needed for that encryption, that particular instance was just a weak PRF. Okay. Yeah, so weak PRF suffices for CPA secure encryption. Okay, so that is one block. Any questions on encrypting one block before we move on to the multiple block situation, which seems to already have created some expectations in some of you. But any questions on the one block sitting? Okay. All right. So how to encrypt a long message? Well, here is something that works. Nothing complicated. No, for those of you know, no block cipher modes. Nothing. You just chop the message into single blocks, into small blocks, and independently encrypt each block. Use the same key. It's what we saw just now was something that's capable of encrypting multiple times using the same key. So we could do that. It'll work. But the problem is that, remember what the ciphertext had? It had that R and the message masked with the pad, right? The pseudo-random pad. The message masked with the pseudo-random pad is exactly as long as the message is. That's one block. The R is another block. So now we have two blocks, which may not sound like a big deal, but if you're downloading a gigabyte of data, now you'll have to download 2 gigabytes of data because ciphertext is double the size of the message. Okay, so we don't quite want that. Well, it would have been okay with that if that was unavoidable, but it's not unavoidable. Why not do the following? So what we need is a PRF or a weak PRF, which takes the same R but produces a very long pad, as long as we want. Okay, so input doesn't change, the output becomes longer. If we could do that with the PRF, we are done. We'll just use that kind of a PRF. So yeah, that's our plan, or that's one of the ways we'll make it work. Get a weak PRF. How do we get it? We'll start from a block cipher. We'll start from a normal PRF. That's what I said. We'll need the block cipher to be a full-fledged PRF. We'll have use for that. But take that and build a weak PRF out of it, which has this extra property that the output length is very long, as long as we want. Okay? And there are several ways to do this. And depending on these ways, you're getting different encryption algorithms, right? And all of them give you this desirable property that the overhead is just one block, because you just need that input to the weak PRF. Okay, so to repeat myself, so there are several ways to do this, and all of them will give you an encryption algorithm where the cipher, to encrypt n bits of message, you'll have n plus k bits of ciphertext, where that k is one block of the, that's the input to the block cipher. Okay, so what are these different ways I mentioned? So there are many actually. I'll only mention a few. And these are called modes of using a block cipher, modes of block cipher modes. Okay, so here's the first mode. Okay, so it just means different ways of using it. So this is called output feedback mode. Here's what it does. So what we want is, has this interface of this big box, right? Takes R, produces many blocks of output. R is one block, so every line here, think of it as one block. So it takes one block as input, produces many blocks of output, and should be pseudo-random. How does it do it? Just feed that first block into the block cipher. Whatever it outputs, output it. Okay? And then, but use that still as an input to the next block. And remember, the inputs to a block cipher are not they don't need to be hidden in some sense, right? They can be, it's okay even if that input is, so input to the second box here, even if it is known, the output looks pseudo-random, output looks random. Okay? So it's okay to reveal the block, unlike in a PRG where if I reveal the seed, I cannot use it as an input to PRG again, and the output won't look random. You can test the output is right. But here, since we have a key, K, that's unknown to the adversary, that's hidden from the adversary, this is okay. Because I'm not going to prove or give the arguments for any of these things, but intuitively, hopefully you're convinced that there's a reasonable idea. Okay? So any questions on the output feedback mode? Okay, okay, so that's it. That's just that. It has some drawbacks. First one is that it's sequential, right? You cannot, even if you have parallel processors, you cannot run it in parallel because you need to get the output from one box before you can feed it into the next box. So you have to do it one after the other. Another, well, not drawback, we are okay with this, is that it's actually a weak PRF, not a PRF. And do you see the reason for that? If the adversary had access to an oracle, it can tell if it is actually doing this or a random function. Just imagine there are 2 blocks, right? The output is 2 blocks long. Okay. So being a PRF means the adversary has control to what it can query. So it can, suppose it feeds an R, first R is say arbitrary, it gets 2 outputs, say A comma B. And now suppose it feeds this A as a next query to the thing. It will give something C comma D. What can you say about this C comma D and the original A comma B? Okay, so let me say that once again. So you feed R, you got 2 blocks A and B. Then suppose you took this A and fed it. You will get C comma D. I'm giving it name C comma D, C and D. What do you know about this A, B, C, and D? So the B that you got was actually by feeding in A. So next time you feed this A, when I said you'll get C comma D, that C will be equal to the B. Right? Does that make sense? So if you feed R, you got A comma B. Well, what is that B? B is just A applied, this FK applied to A. So if you feed A now, you get C comma D. C is also FK applied to A. Okay? And this wouldn't happen with a random function. You feed it R, it gives you A comma B. You feed it A, it will give you, B comma something will not happen with a random function except with negligible probability. So you can tell the difference, right? So it's not a PRF. Here is the attack, right? But it is a weak PRF. Okay, so that you have to take my word for it. Here's another approach, okay, so that you actually get a PRF, not a weak PRF. Not that it matters, but why not? Here I split, actually this R is a little shorter than a block. Okay, let's say the last, 20 bits of this R, if the original R was say 128 bits, this is only, let's say 100 bits. Okay? So set aside some 28 bits. What am I setting it aside for? I'm setting it aside for this counter. So when, I can go, so I said I set aside 28 bits. So 2 to the 28, like, almost a billion. I can get that many blocks here where this 1, 2, 3 up to T are just 28-bit integers, right? So I append them to that R, which is only 100 bits. Okay, so I'm basically applying my PRF, the original PRF, to several inputs that are derived from the original input you gave me. Okay. And this can be done in parallel, so it's actually nice. It can be done in parallel. It's also PRF. Okay, because you only get to ask for 100-bit string, like you change that, the whole, the 2 to the 28 things you're querying here on will change. So it is a PRF, not just a weak PRF. It does have a couple of drawbacks. One is that the input length shrunk a little bit. Instead of 128 bits, now it's only 100 bits. It might be okay. We relied on the input being so long to say when I pick something at random, there are no collisions. But 100 bits is still okay. Another drawback, though, is that this a priori limit. You have to set aside this 28 bits for this purpose, or whatever number of bits, and you cannot go beyond that. Okay? It's not that you cannot go beyond that. Then you need to use a fresh R for the remaining. So the message, there's like an upper limit on the message length that this can take. Okay? Still a reasonable option. What's used a lot in practice is not quite this. A slight variation of this, which is a little more flexible, which says, okay, take your R, which is whole 128 bits long now, and so you don't have space to pad anything there, but just keep incrementing. Okay, so think of R as a bit as an integer, just keep adding to it. So R plus 1, R plus 2, up to whatever number. Okay. Use those as the inputs to your individual block ciphers. And this is almost the same as this, but now this is not a PRF, it's only a weak PRF. It's for the same kind of reason we saw with the other one. Somebody can query this whole thing with R versus R plus 1, you will see that there are a lot of overlap, right? So it's not a PRF, but it's a weak PRF. There is some sort of an assumption here, not quite a standard weak PRF because there's some upper limit on, there's no explicit a priori limit on how big this T can be, but there is an implicit limit saying that, look, when I pick an R at random and then you pick a T that is allowed, like as big as you can handle, there shouldn't be any overlap between this R plus 1 up to R plus T and the new another R prime plus 1 up to R prime plus T, right? So they shouldn't overlap. But it's kind of a more flexible, you don't have to priori say, oh, my T is 120, or whatever, 2 to the 28 or anything. So this is called the counter mode, or the CTR mode for counter. And that's kind of a standard. That's what's used most. All of this, I described them as PRFs or weak PRFs. To use it as encryption, you do need to XOR them block by block, XOR the outputs of this pad block by block with the blocks of the message. Right? So that's all these modes. Now there are some modes that don't quite fit this template, and they're kind of there for legacy purpose, you could say. So in particular, the most common one is cipher block chaining, or CBC mode, invented in 1976, before there were any definitions of security, like we have today. And the notion of a block cipher was that it was actually an encryption algorithm. There was no you feed the message itself. You could potentially feed the message itself into the block cipher. So the CBC mode has this architecture. It doesn't quite matter if you don't have to memorize it, but it's basically cipher block chaining, right? Cipher blocks are chained. It feeds into the next block or box after XORing with the next block of the message. Okay, so some slightly complicated thing. It's not very immediately clear that this is secure. It can be proven secure, but the proofs came much later than only after definitions were there. So originally it was just some ad hoc way of doing it, and it has its limitations. One is that encryption is sequential. Decryption, though, is parallelizable, because to carry out the decryption, which is going back, all you need is a previous ciphertext and the current ciphertext block, and you can get the current message block. However, I said going back. So it needs this facility that with the key, I should be able to invert the block cipher. I should be able to compute the function backwards. This is one of the reasons, even now block ciphers have this facility. It's not really needed for, at least not for mainstream purposes like encryption. You don't really need to invert the block cipher. So none of these operations, right? You need to invert the block cipher. In CBC for decryption you do. There are other minor issues like you need an integral number of blocks. So if I wanted to only send 1.5 blocks of message, well, still you'll need to pad it up to 2 blocks of message, and so that there are 2 blocks of ciphertext in addition to the nonce or the R. Okay, yeah, it's a good place to point out this kind of, some confusing terminology. So if you look at how block ciphers are described, and you go online, Stack Exchange, wherever, a lot of the terminology is confusing or misleading, and that's not just on the internet. I mean, that's how the standards has kind of become the language in that literature, because these are things from the 70s carrying forward. So first of all, applying the PRF is called encryption. And that is there's a deterministic operation, is applying the PRF, but that operation is called encryption. Okay? It's not encryption, doesn't meet our CPA security definition or anything, but that's just the legacy terminology. Inverting this is called decryption. For our purpose, for decryption, we never needed to use decryption in this sense. We always were using encryption in, say, anything other than the CBC mode, right? But inverting the PRF, computing this FK inverse, is called decryption. Input to the PRF, which was our R in, say, the counter mode, I said we could call it the nonce. It's called the plain text, and the output is called the ciphertext. Okay, so this just kind of made to look like a block cipher is doing encryption for you, feeding your plain text, you'll get the ciphertext out, and it has a name for doing this kind of thing. It's called the electronic code book mode, and you'll see today afternoon. It's not a secure encryption scheme at all. It's just a way of using, a way of running your PRF. Doesn't result in encryption. Okay, I think let's see how we are doing on time. Have like half an hour, a little more than that. So let's just try authentication. Okay. Again, we will be in the symmetric key setting, what's authentication? When you send a message to someone, they need to know that it came from you, and they have already shared a key with you. That's the setting for today. So they know, in that sense, they know who you are. They just want to make sure this message is from you. Okay, so that's integrity. Like you don't want somebody to claim that I'm authorized to send this message, and here is my message. Right? You should be able to detect that it's not an authentic message. But it's not just that an authentication or integrity is separate from confidentiality. In higher level applications, if you don't have integrity, you probably won't have confidentiality either. Just to kind of give you an example, somebody sends you a message saying, here's my new email ID, send all further emails to this ID, and you start sending them all the messages. If that is a spoofed message, well, your confidentiality is gone. You're sending your messages to someone else other than the person you meant to. You might think that, okay, that sounds like that's because there is no encryption. When there is all this encryption going on, it would automatically give you some way to check that the message is coming from the other person, right? After all, you have a key, and when somebody sends you an encrypted message, you're going to pass it through this decryption algorithm, which should somehow be able to tell you if this was just a bogus message created by someone who doesn't know the key. Unfortunately, that's not true. To give you an example, so if you have the counter mode, for instance, think of just encrypting one block here. Somebody could take a message that's being sent, and a ciphertext that's being sent, and change it into ciphertext of another message, a meaningful message potentially. So an encryption of M can be changed to an encryption of M prime, where M prime is obtained by XORing M. So you may not know M, but you know that this is a message with certain structure. I think here there will be some particular string. I want to change that string to this other string. Well, you can do that by XORing the message with something which is 0 everywhere, but at that place it has a XOR of the two, the original message and the intended message. So that says D, the difference. You apply, so you want to change M to M prime, where M prime is M XOR D, for some D of your choice. You can completely do that because all you do is that XOR this whole thing, the second piece, here with this D. Okay, so you apply your D that was meant for the ciphertext meant for the message onto the ciphertext. It will have the effect of changing the message underlying this encryption. This kind of property is called homomorphism of an encryption scheme. Okay? But here it's a problem. Right? So encryption by itself doesn't give you any sort of authentication guarantee. You could, of course, very carefully design some modes of operation for a block cipher which would do that. But for that you need to do that. That's exactly what we are going to talk about, or one of the things we'll talk about. Okay, so forgetting encryption for a second, just thinking about authentication. The tool that's used to, just like we have encryption as a scheme, a cryptographic scheme, the corresponding thing for authentication is called a message authentication code, okay, or a MAC. Okay? So of course MAC is a acronym with different expansions in different contexts. Here it means message authentication code. Okay, so what we're going to do in the remaining time is, well, actually, let me kind of put it together with what we already did. We already have CPA secure encryption, right? Using, say, block cipher in a counter mode. So we're good with that. It doesn't offer any sort of authentication, though. What we are going to do now is figure out how to build this MAC. And we'll do that also from a block cipher. Okay, so we'll have both encryption and authentication. Often, okay, there's another thing which we'll not talk about today, which is hash functions. They are relevant to some constructions of MACs. Not all MACs need it. The one we are going to talk about today won't need it. But some constructions do use something called hash functions, which we'll define tomorrow. Yeah, so forget hash functions for now. So you have, we'll have encryption, we'll have MAC, and we can put them together to get authenticated encryption. And the simplest way to put them together is encrypt then MAC. So you create the ciphertext and put so MAC, the syntax we'll see in a second, is to create a tag and put it alongside the message that you're authenticating. Okay? So outside of the ciphertext, you put a tag, say, which is your authentication code, the tag from the MAC. Okay, that's what encrypt then MAC means. You could do other things which are not necessarily guaranteed to be secure. For instance, MAC the message and then encrypt the whole thing. That might sound like a better idea. It is more vulnerable because the encryption algorithm is not tamper-proof. It allows certain kind of seemingly innocuous maybe changes. Even with the MAC on it, you can change the ciphertext in a way that doesn't really change the message inside, and that's actually can be a problem. So the safest way to do this, or simplest way to do this, is encrypt then MAC. Now that's not quite the standard way of doing authenticated encryption. You can do it more efficiently. I'll mention it actually today, and if I have time, we'll see a little bit tomorrow. When we see hash functions, we'll talk a little bit about authenticated encryption also. Okay, but if you're not worried too much about, when I say efficiency here, it's about the computational efficiency. In terms of the size of the messages, which is what really matters for communication, right? That's all the messages being sent over the network. These are all, the encrypt then MAC is as good as anything else. Okay, but if you want to save on computation, then there are better schemes. Okay, okay, but the bottom line of all of this would be that encryption and authentication can be entirely based on, symmetric encryption and authentication can be entirely based on block ciphers. Okay, so this is a magical tool that can give you all of this. There are, of course, I didn't mention how hash functions fit in. That's a tool that can be used to increase efficiency and for other purposes. But for just this, if you want to get this working, block ciphers are good enough.